Okay, we now know how to figure out the number of protons and total electrons in an atom, since the atomic number, the number in the top left of the periodic table block for that element, tells us the atomic number. So, for instance, for beryllium, it's got an element block like this. Okay, and up in the top left, we have a big number 4, which is our atomic number. Which tells us we have 4 protons. And to match it, we've got 4 electrons total in the atom. Okay, so the last thing we haven't figured out is the number of neutrons. And this is a little bit tougher because, well, they're neutral, they're not charged. So we know that the protons and the electrons have to kind of match numbers so that way we can cancel out all the positive charge with negative charge. But then if the neutrons aren't charged, they don't really need to be canceled by anything. So we can have a lot of different versions of the same element with different numbers of neutrons, okay, just by kind of what shows up in this kind of world of atoms. So it becomes a lot harder to predict, and we don't really have just a list of all the different versions of how many different neutrons an atom can have on the periodic table. So the periodic table alone here cannot help us figure out the number of neutrons. What we need instead is to get something to tag this specific version of an element. Okay, now the version of an element that we're kind of talking about has another sciencey name. It's called an isotope. So isotopes are just different versions of atoms that have a different number of neutrons. So it's the same element, it's got the same number of protons, but the neutrons are kind of mixed up. So if we had an atom of beryllium with 4 protons, maybe it has 5 neutrons, okay? Or maybe it has 4, or maybe it has 6. Some elements only have one version, like beryllium is actually one of those. It only has a version of itself where it has 5 neutrons, and there's no other options. But other elements can have upwards of 20 or more different versions, different isotopes. Like carbon can come in the forms of carbon with 6 neutrons, or carbon with 7 neutrons, or carbon with 8 neutrons. Okay, so it's not something we can just predict easily. Instead, we need to work backwards from some tag that we put on that isotope to say this is how many neutrons are in there. Okay, the way that we do that is with something called the mass number, and that mass number either shows up in an atomic symbol or an isotope name. That's pretty bad. So let's start with the isotope name because it's a little bit easier to understand. Okay, we basically just speak out the element and then do a little dash and add a number after it that tells us what that mass number is. Okay, and to be more specific, the mass number is the number of protons plus the number of neutrons. All right, that's also written up here. I think I'm actually going to get a different color of blue. That's better. Get something a little bit lighter. Oop, I forgot to actually change it. Neutrons. So the number of protons plus the number of neutrons is what gives us the mass number. Okay. Well, in an isotope name, we just write out the name of the element like we normally would, like, say, carbon. Carbon. All right. Then we do a little dash. Right? And then we write the mass number after it. Okay, that number of protons plus neutrons. Okay, so maybe I have a version of carbon called carbon 12. Okay, I could backtrack and figure out how many neutrons are in there, since that number 12 has to be equal to the number of protons plus neutrons. If I go and find carbon on the periodic table, it has to have 6 protons, or else it is not carbon. So then the question is, how many neutrons must this have? 6 plus what gives me 12? Okay, or if you wanted to rearrange this a little bit, if we have the mass number and we want to find the number of neutrons, we just have to subtract out this number of protons. Our protons and neutrons together minus the number of protons leaves us with just the number of neutrons. So generally, mass number let's do red, minus the number of protons is going to be equal to the number of neutrons. Okay, so in the case of carbon-12, this would end up needing 6 neutrons. Okay, if we had a version of carbon called carbon-14, then we'd have to go with that mass number of 14 and say, well, it still has 6 protons because it's still carbon. All right, so 14 minus 6 would leave us with 8 neutrons in that version. Still carbon, but it's got a different mass because it's got a different number of neutrons. Okay, so that's how we can write it out as an isotope name, right? And we call this the mass number because the protons and the neutrons are the most massive things in an atom. The electrons are very, very light in comparison. Okay, so the mass is kind of related to the number of protons plus neutrons. So we just kind of group that together and call it the mass number. Okay, now we can also write this as an atomic symbol. Okay, which looks a little bit more complicated, but it's really the same information. Instead of writing out the element, okay, we write the symbol instead of the name. Okay, so whatever it is on the periodic table, like for instance, carbon would be big old C. All right. They call the mass number A here, but I mean, you can kind of call it whatever to make it kind of make more sense to me and hopefully to you. I'm going to call this M for mass number. And then down below, we have the atomic number, which is just the number of protons. I'm going to call that little a. Okay, so in the top left, we're going to write the mass number. Okay, so like if we're doing carbon-12 still, that 12 is my mass number, the number of protons plus neutrons, and I write that up in the top left. Okay, and then just my number of protons, the atomic number, goes down in the bottom left. Okay, so just a different way of writing it. So you can either do this as an isotope name, like this. Oop, I went through my symbol. All right, as the isotope name like this, or you can write it as the atomic symbol like this. Now, something you have to be careful of, we're used to looking in the top left for the atomic number. So you might think, okay, well, the atomic number is going to go in the top left here, because that would make sense. But instead, we kind of switch it up, and it now goes in the bottom left. Okay, our mass number goes in the top left. And there's a helpful little reason for that that we'll see down below when we start trying to figure out the number of neutrons. Okay, so mass number goes in the top left, atomic number goes in the bottom left. Okay, and in the name, the mass number goes after the dash, after the element name, and we don't need to write the number of protons because we can just go look up the element anyway. Okay, let's look at some examples here. All right, so first up, I'm looking at a version of the element magnesium. Okay, and I have an atomic number of 12. Again, that's the number of protons. Okay, so if I go and find magnesium Mg on the periodic table, it does indeed have 12 protons. It's got an atomic number of 12, which is good. That checks out. Okay, and this specific version of magnesium is said to have a mass number of 25. Okay, oops. Where again, that mass number is the number of protons plus neutrons. Okay, so this 25 is P plus N, protons plus neutrons. Okay, so if I wanted to figure out how many neutrons are in this, I could say, hey, I've got a mass number of 25 protons and neutrons minus the 12 protons. That leaves me with 13 neutrons. Okay, so my mass number minus my number of protons is equal to my number of neutrons. All right, to write the atomic symbol for this, again, mass number goes up on top left, and atomic number goes on the bottom left. Oh, that was a really bad arrow. Let me try that again. That's better. Okay, and the symbol for magnesium is Mg. Okay, and then if I wanted to write it out as a name, I would write magnesium with a dash, and then my mass number is 25. So again, my mass number, that kind of shows which version of the element, which isotope I'm dealing with, is in both the atomic symbol and the isotope name. And it kind of has to be, because otherwise we can't figure out how many neutrons are in there. Okay, let's look at an example where we're missing some information. So all I know about this next one is that I'm dealing with atomic number 51, and that the mass number of this version of whatever this element is 123. So I have 123 protons and neutrons together in the nucleus. Well, let's see. If we have 51 protons here, I could actually figure out the element just with that, okay? Because that's the only thing that determines the element. So if I go and find number 51 on the periodic table, that is symbol Sb, which is the element antimony. Right? I don't know which version of antimony we're dealing with until I tag on that mass number. Okay, so we're dealing with this isotope, this version of antimony, antimony 123. Okay, now I could also figure out the atomic symbol just with this. Sb, whoops. Sb is my element symbol. My mass number is 123. Okay, and my atomic number for antimony is 51. Okay, but I still need to figure out the number of neutrons. Okay, so if you can remember this, that you take the mass number, which is protons plus neutrons, and subtract out the protons, you can get the neutrons, and we can do that. But here's the reason why I like the atomic symbol and why it's set up like this with the mass number on top. Okay, if the number of neutrons is the mass number minus the number of protons, this is actually set up kind of like a subtraction problem. So if I take 123 minus 51, that should be my number of neutrons. Okay, it's like already built in there to subtract it out to find the number of neutrons. Okay, now if you've got some good math skills, you might be able to work this out by hand, but I would rather use a calculator. So let me pull that up. 123 minus 51. What I'm left with is my number of neutrons is 72. Okay, and you could also do this by doing it kind of in a line like this. Doesn't matter, as long as you take the mass number minus the atomic number. I just like this because it's a nice reminder of getting the numbers right, so you're not adding or subtracting weird. Okay, let's do another example. In this case, all we know is that the element is bromine and that its mass number is 80. Okay, so some things I can write right off the bat. Well, if this is bromine, I can go find bromine on the periodic table. There's a lot of elements that start with B. There's Ba, and there's Be, and there's just B, and there's Br. Ooh, Br is bromine. All right. Our isotope is tagged with this mass number 80, so that's our mass number there. 80. All right. While I'm looking at bromine on the periodic table, it's got its atomic number in the top left, which is 35. So it's got 35 protons. All right. So now I can write its atomic symbol. I've got Br. All right. So our mass number of 80 is going up in the top left. Our atomic number of 35 is going down in the bottom left. Then, this is already set up for the subtraction. Mass number minus the number of protons leaves us with the number of neutrons. And this one I can do in my head. This should be 45. Okay. So this version, this isotope of bromine has 45 neutrons. Okay. Now, what your assignment is mostly going to be like is something down here like this. Okay, where we want to figure out the number of protons, neutrons, and electrons in a specific isotope, either from the isotope symbol or the isotope name, or we're going the other way around and we're trying to figure out what to call the isotope based on the number of protons, neutrons, and electrons. So let's do these real fast. So in this case, we've got a mass number of 20 and an atomic number of 10 for this isotope of neon. So that atomic number of 10 means I've got 10 protons. I don't even need to check the periodic table for that one because it's right there for me. Okay, that means I've got to have 10 electrons to match those 10 protons. And to figure out the number of neutrons, I've just got to subtract. Okay, let me move this out of the way a little bit so I can do my little subtraction setup. 20 minus 10 is going to leave me with 10 neutrons. That's kind of nice, they all match, but it doesn't happen like that all the time. In this next example, neon has a mass number of 22. So same element, but different number of neutrons. Well, if it's the same element, it's still neon. I can go double check on the periodic table, but it's still going to have 10 protons. Whether I'm finding that from the atomic number here or finding it on the periodic table, neon has to have 10 protons to be neon, which means I still have to have 10 electrons to match that. Right? The last thing I need to figure out is the number of neutrons. So if I have 22 protons and neutrons together, and I subtract out my 10 protons, what I'm left with is 12 neutrons in this version. Okay, now in this last one, I've got all the information I need. I just need to write out the isotope name or the isotope symbol. So let's start with the name. All right. Well, hey, this one has 10 protons also. So this is still neon, and it's got 10 electrons to match. So this is neon. Neon. I just need to tag it with its mass number. And the mass number is the number of protons plus neutrons. In this case, they just gave me the number of neutrons. We have 21 neutrons. All right. So 10 plus 21 is going to be my mass number, my number of protons plus neutrons, which winds up being 31. So this is the isotope neon 31. And if I wanted, I could write it as a symbol where I've got an E to stand for neon. My mass number of 31 goes in the top left. And my atomic number of 10 goes in the bottom left. And I'm good to go.